Stars are whispering tales of old, planets spinning, stories bold. Life is dancing through the night, countless worlds in the starlight. Galaxies full of mystery, infinite in their history, beyond our dreams and our sights. Life blooms in the cosmic lights, dancing on the edge of space. Take me away, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Nebulas with colors bright, birth new wonders in the light. Comets trail their sparkling tears, life endures through the years. In the silence of the void, every heartbeat is enjoyed. From the depths and to the heights, life expands through cosmic night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night.
Hey everybody, welcome to SkyTour Livestream. It is me, Mark D'Antonio, you know, that same old annoying guy, along with the other old annoying guy, Daryl. Hey Daryl, how you doing?
Well, hello, Mark. I'm okay. Thank you for asking. Hello, everybody. Hope you missed me. I missed you.
Daryl,
Hello, Genghis.
you feeling okay?
I am doing relatively well at the moment. This, whatever the heck I've got, it keeps coming back on me, and
We don't want that.
you're telling me. I mean, I'm doing pretty good at the moment, so here I am.
All right.
And hello, everybody.
So, you know, you and I were talking off the air before we started. You wanted to take the reins for a couple of minutes to tell folks some things, and I wanted to give you that opportunity.
Okay. I don't know if you'd want to try to manipulate Stellarium while I say
Yes,
what
I
to
can
say.
certainly do that. That's a perfectly good idea.
Over in the west, southwest first.
Yeah. First, I'll show people where we are. We're actually, see those beautiful bright stars. This is we're actually up in Taurus. We're up in this region right here. This is the Hyades, which is that beautiful V-shaped cluster of which Aldebaran is not a part, but I think Daryl's probably going to say something about that. But where do you want to start, Daryl? I'll start here.
Well, sure, you can start there. You see that V shape, folks. Aldebaran, you can say he doesn't really belong to the cluster, but he's in the same field of view. So let's say he belongs to the Hyades. That V shape is the head, the wedge shape there is the head of Taurus the bull. And his horns extend off out of frame to the left. And you see Jupiter there over to the left of Aldebaran. And this entire apparition of Jupiter's been in Taurus all this year. He's been moving back and forth, kind of dancing back and forth in between the horns of the bull. He was out all the way near Elnath out there toward the end of the tips of the horns. And now he has backed up almost to the V again. And what you're seeing there is planetary motion in action, and us passing Jupiter a while back when Jupiter went through opposition. And instead of direct motion moving west to east as planets generally do, well, we saw the planet moving east to west again, backing up into the Hyades, because as Earth passed Jupiter, we see Jupiter falling behind all of a sudden. Now, this is just a matter of perspective. This is like watching road signs on the highway and other cars around you. You know, you pass a car, he's still going fast, but he seems to fall behind you for a while. Then eventually he'll start moving forward again. And it's all just a matter of your perspective from your position, what car you're driving, what planet you're on. Yep. So instead of direct motion, it's in retrograde motion. I suspect it's going to start moving back in direct motion again here fairly soon, at which time it will, moving over toward Gemini, which is where Jupiter is going to be living next year. And while we're in the area, can you just go ahead and move on over to Gemini? Okay, you see there's Mars down there at the bottom, and that's Pollux right next to Mars, and the other twin's head is Castor right there. Castor is the upper one, Pollux is the lower one, and there's Mars right next to it. Now, all the planets are doing a really cool dance in the skies right now, and you've doubtless heard about the planetary alignment, and they're all kind of queuing up in place, but they're dancing on their own anyway. Mars was all the way over in Cancer, down there at the bottom of the screen now. When Mars was at opposition, it was in Cancer, and that same retrograde motion, because Earth passed Mars, is making Mars appear to move backwards in the sky now, and he's all the way back in Gemini again. And if I remember correctly, because of Mars' proximity to Earth, Mars shows the greatest retrograde motion of any of the planet, well, any of the superior planets at any rate. Yeah, and Mars too will eventually start moving in direct motion again, prograde motion, west-east across the sky. And at which point he's going to be chasing Earth for the next 2 years until the next opposition happens, 26 months.
That's it, yeah.
And just real quick, can you go over to the western sky?
Yeah, that's where I'm going, because we want to show, well, we have Uranus and Neptune up here too, but we also have Venus down in the west, right here, with Saturn.
Yep, and this is the other one. It has been cloudy here. I managed to miss it. Saturn passed Venus, was in conjunction with Venus some days ago, maybe last week, at which time they were closest together in the sky. And Saturn is now moved past Venus and is dropping lower night by night, about to disappear into the sunset. Venus on its own just recently uh, it rounded the corner in its orbit as we see it from Earth, because Venus is closer to the sun than we are. Well, we've seen it march up from the sunset for months and months, getting higher and higher in the southwestern sky, and it just rounded the corner in its orbit and is now dropping back toward the sun again. Venus was at a half-lit phase. It looked like a first quarter moon, except it was tiny, much smaller than the moon. And it's turning into a crescent night by night now. The Venus is rapidly moving closer to us because we're on the same side of the orbits now. And as you see there, Venus has shrunk from a half-lit to a crescent, and it's going to get bigger and bigger and skinnier and brighter night by night until Venus passes through what's called inferior conjunction with the Sun in March, if I remember correctly, March 22nd or 23rd, at which time it will be as close to us. Venus is about the same size as Earth, actually just a little smaller, but at that time it will be about 1 arc minute in diameter, or about 1/30th the size of the moon in the sky. And I don't know yet if it's going to happen this time or not. Sometimes after a few days after the very last new moon, before Venus goes through inferior conjunction, you will see a beautiful skinny crescent Venus sitting right next to the moon. And if you're lucky, sometimes you can even catch it in the same field of view of the telescope, at which time you'll see a great big crescent, which is the moon, and a much smaller crescent right next to it, showing exactly they're really close to the same phase.
I really want to do that, but I don't think it's going to happen this time that we'll be able to catch it in the same field.
Yeah, so it goes. I've seen it twice, 2 or 3 times in my life.
It's amazing.
It's an amazingly striking thing to see.
It is. When you see these crescents, it's like, you think back, anyone who saw those phases of the moon and then saw the phases of something else in the sky, if they didn't know, and they didn't originally, about the orbits of the other planets, this would be very perplexing to them. They didn't actually understand what was going on. They tried to explain it with weird constructs, from Ptolemy all the way on out, and it was actually a pretty turbulent time astronomically wise, and so they tried to explain things using astrology, which of course was even more ridiculous, But
yeah, well, and what Mark means about those motions, where they do move from direct motion to retrograde motion, they describe loops across the sky.
Yeah,
they'll be going forward, and all of a sudden they'll stop and start going back, then they'll start going forward again, and they make little loops in the sky, which the ancients could not explain.
Yeah.
And this is where the idea of epicycles came from,
right.
And the idea of a clockwork universe.
Ptolemy and his epicycles. And what's interesting is the distance, the size of the Earth's orbit, around the sun, is directly projected on the retrograde motion of Mars, and for Jupiter it's smaller. So the size of Earth's orbit, as seen from Jupiter, is approximately what you see in the sky. From Jupiter, that's how big our Earth's orbit would look like to it.
That's an interesting point.
And that's kind of interesting, too, because it shows you just how big and how far away. But you know what? We're not exposed to the size and projections of these retrograde and prograde motions on the sky. So we don't see them when we look at a normal sky. We see a red dot in the sky. We call it Mars. You don't see the entire cycle unless we take pictures and draw lines and actually have a graphic to show you. So when you see the retrograde motion of Mars, you're actually seeing a projection of the Earth's orbit all the way out at Mars, and that's how big Mars would be, or that's how big the Earth's orbit would look from Mars. So it's exactly the same thing. So geometrically, it's a direct geometric proportion. So the smaller the size of the retrograde and prograde motion that you see, that little circle in the sky Daryl was just talking about, the more the more you're looking at how big the Earth's orbit looks from that position. It's exactly that size. So you could say, oh, I'm on Mars, and you look toward the sky and you see the cycle in the sky. You see that circular backpedaling and then forward pedaling of the planet, and say, oh, I'm looking at Earth's orbit from Mars, because you really would be. It's the same exact thing. It's just you're at the opposite side of the line.
Interestingly, when Halley's Comet came through back in 85 and 86, well, it passed closest to Earth, God, I forget, March 21st or early April. I think it was late March. And it was then moving away from Earth. And I remember watching it at the time. It was way down in the southern sky. And then it started rising again. It got down into Centaurus, and then it came back up under or the Crow in the crater, the Cup, near Virgo. And projecting that on a map, it did the exact same thing. It went up, and then it made a little loop and kept going up, and it made another loop. Each loop was a year on Earth, and I've seen runs of Halley's orbit, Halley's apparent motion in space as seen from Earth, and well, it goes loop, 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 loop. Each loop smaller than the last as it moves back out in its orbit farther away from us, and that's the end result is exactly the same. That's Earth's motion affecting our point of view. Karen, I can't easily show a retrograde motion. If somebody worked with, I don't know if Stellarium will do it or not. It's out there.
I don't think Stellarium allows you to lock onto a planet and take it through a year and trace the result. That'd be great if it did. I do know a program that does do that, and that's Universe Sandbox. We could do it in there.
Sometime it'd be neat to do that.
Yeah, we could generate the entire year and watch the planets go through their cycles, as seen from the Earth. Yeah.
Okay. And as far as the alignment goes, the big alignment, well, it's missing Mercury. Mercury, at least last I knew, was still in the morning sky, so it won't be joining until later on.
Yeah.
Maybe whatever date they're saying. Maybe it will be back in the evening sky by then. But it's just, the alignment doesn't really mean anything. It's just all the visible planets, except for Mercury now, are visible in the sky from east to west after sunset right now.
Yeah.
Mars is up, and then Jupiter, and then Uranus and Neptune are up there somewhere. And I've never cared too much for looking at them. You can look at them in a telescope and say you saw them, just to get it off your bucket list. But
well, we did look at Uranus the other night.
Yeah.
We saw Titania and Oberon. We saw the moons.
That's cool.
And we saw I think maybe you were lurking. I'm not sure, but we could see the color of Uranus if we knocked down the exposure significantly.
No, I wasn't lurking. Was it green?
It was sort of a teal.
Yeah.
Yeah.
So you got to say you saw Uranus. And Neptune is much the same.
Yeah.
Uranus is actually visible naked eye. It's very dim, and the ancients never noticed Uranus as one of the classical planets because it was just too dim, even if it was visible. Visible. They just didn't notice it because it's so dim.
Yeah.
But anyway, you'll see from Mars in the east to Jupiter, then now Venus, and now Saturn has swapped position with Venus. So this, you just still see them stretched across the sky.
This is the line right here. This is that planetary alignment everyone's talking about. Here's Mars, as Daryl just told you. There's Jupiter. Okay. here's Venus, and here's Saturn. Now in here is Uranus and Neptune. We looked at Uranus the other night, and Neptune is out here too. Neptune looks markedly blue, and we can see some of its moons as well. But again, this is not. This is a wide field telescope. It's not the kind of telescope that's ideal for looking at planets. I did start outfitting another computer so that when we get the Celestron 11 into its new home, hopefully, we're going to have a field that's 33 by 22 minutes of arc in size. And that's with a 0.7 focal length reducer. Takes us down to from 2800 to 1955 millimeter focal length, which means a slightly wider field. It's going to increase the speed of the telescope by about 2 times. So we aren't going to be as fast as this telescope, but we definitely are going to be able to record some pretty cool things.
Could you go back to that view, all sky view?
Yeah, sure.
As Mark was just saying, if you see Mars there, and then, well, you see that red line. Leave that right where
Oh,
it
yeah,
is.
okay, so you like that. That's the ecliptic.
Yeah, that's the plane of the ecliptic.
Yep.
Strictly speaking, that is the path of the sun across the sky, but that's also describing Earth's orbit around the sun.
And the plane of the
as
solar
we
system.
sit. And it's the plane of the solar system with a little variation. You see Mars is a little above the plane, Jupiter's real close, and Venus is a little bit above, and Saturn is close. The planets are all on average on or close to the plane of the ecliptic. That plane that literally is where eclipses happen. That's also where the planets run across the sky. And they're the highest the plane of the ecliptic ever gets is 23.5 degrees north of the celestial equator, and the lowest it ever gets, like over in the west, is 23.5 degrees below the celestial equator. And that's what defines the tropics, the Tropic of Cancer and the Tropic of Capricorn. Let's just stop there. I could just run off the mouth all night.
That's funny. No, but still, that's pretty cool. But this is our sky tonight. This is the winter Milky Way you can see here. This is only a 12-second exposure. You can see we have a little haze at this end. We have the lights of Phoenix here, about 80 miles to our southeast here, actually east-southeast. And the sensitive camera allows you to see those lights. When you're there, you cannot see your hand in front of your face, but you can definitely see these lights when you have a sensitive camera. And that's something that we live with. And in the Benson Observatory, this sky is actually a little bit darker than what we're seeing here. It's pretty nice, actually. The Milky Way has much more definition and detail with the naked eye. You look at the naked eye of the Milky Way here, and you can kind of see the star clouds, and you can sort of see the definition of the dark nebula, the dark clouds of dust. But in Benson, it stands right out. You cannot miss it. So that's why we're so excited about trying to get our telescope out into Benson at that in that new site. So we're gonna see if we can go for it, and I can't wait to see what we come up with.
One word.
One word.
Planetary camera.
Uh-huh.
That's 2 words, but
Yeah, actually, I was actually thinking of doing a piggyback wide field camera to show the entire sky, so we could do a major panorama. I mean, like 30 degrees by 30 degrees kind of a thing, and then doing the regular telescope, and I would put we do have an off-axis guider system we're using for this new system, and that's a special kind of guider, so it needs a little bit different material. I started outfitting the computer that we would theoretically put into the new observatory today, and I got it all set up today. So it's ready to rock and roll, and hopefully it'll do well. Hopefully it'll do very well. I do want to say hello to folks that are here, and I have to say that Tim F was the first one. Hey Tim, Tiffany's with us. Hello Tiff. And of course we have Kieran Belmont decided to join us tonight. That's wonderful. Thank you. Mr. Django in Belgium. How you doing, brother? Daisy and Zoe Amethyst. Catherine Messick, how are you? And Michael Galea is with us. Nice to see you, brother. And we have with us as well Stuffy. We have Cosmic Ray, who's playing with his C-Star telescope. And Sam S is joining us. Genghis is with us. Kurt W75, nice to see you as well. Epic
Isabella's
TV,
here.
huh?
Isabella's here.
And Izabela, yeah, excellent. Epic TV, that's Anthony, a good friend of mine. Anthony's got a really cool. Look him up on YouTube. Anthony does some really cool investigations of UFOs and so forth. That's Anthony with Epic TV. Okay, and then we have on top of that we have I saw C&D boy. There he is. I think his name's Doug. You know what? My mind's going blank. Sorry. Okay. And Rock is with us. Rockstar, Genghis, Izabela. Hello. Good to see you, Izabela. And those are the early birds. Hopefully we'll see some ones later that want to join. But okay, so here's the all sky right now. This is our view, and currently we're looking right here. We're looking at this little section of this V that Daryl was just telling you about. Okay, this is Aldebaran right here. And this is the V. We're just around, we're like here. Looking at this, our field is about this big. It's a tiny little view here, but it corresponds to about 1.5 degrees by a degree tall, right? So that's neat. So we'll put this away for a moment and come back to our stars. Here you can see that I've got them really enhanced right now. If I drop these down, okay, like to here, then you can see the stars, and you can see these beautiful blue and orange star. It just looks beautiful. And this will be, yeah, I already took a picture of that. Let me just make sure I saved it as well. All right, good. All right. So that's just the Hyades, the little section in the Hyades that we're looking at. And then we're going to look at a lot of other things tonight. We're in the neighborhood, so we might as well check out Messier 1, which is going to be very high in the sky. And it might actually be quite showy tonight. We might see some real detail. So why don't we check that out too? There is a comet, as Cosmic Ray pointed out. It's near M1, which is the Crab Nebula right here. Right? But it's just very dim. I don't know if it will be in our field. I'm not sure how far away it is from Messier 1. I haven't even looked. I'm just going on what Ray says. But we'll take
What is
some.
that star's name?
What star?
That star.
Tianguan.
Tian?
Tianguan.
Tianguan?
You got it.
Okay. I never can remember its name. And
Tinguan. Call it Tinguan, like penguin. Tinguan.
Right. Well, that's the other tip of the bull's horns.
That's right.
Elnath is the other one, and then it's right next to the Crab Nebula.
You got it. Yeah. All right, so we'll check the Crab Nebula out now. Being that it's fairly high in the sky, I think it might look really nice. So we'll turn that off. And let's go back to bringing this telescope over there. You'll watch the telescope move now slightly over my head. You see it go there. Really nice. And we should see a little fuzzy guy show up here. Yeah, there it is. Ooh, hey, that's good placement. Right off the bat. Dead center. Right, and I think our focus might be good as well. I'll zoom in and check it out, because I had done a critical focus earlier, but I want to see if it's changed any. Oh yeah, it's changed a little. Alright. Temperature out in the building right now is 7.9 or 8 degrees Celsius. So it's actually a little chilly out there. Alright, so what we're going to do is we'll just go positive here. Just enough. so that we can capture critical focus.
How much is that in freedom units?
Freedom units. I don't know.
What was the number again?
What numbers?
Well, the temperature.
Oh, 7.94 Celsius.
Okay.
So we're
So
looking at
it's
36.
More than that. 10 degrees Celsius is 50 degrees Fahrenheit.
Okay.
So you're down in the 40s.
Mm-hmm.
We have a few metric members in chat, I'm sure.
Yeah, we do.
Django.
Mr. Django, yeah.
Izabela.
They are smart. They're using the smart units. We're using the stupid units.
I'll argue that till with my last breath.
Karen Models with us. Hey, Karen. Good to see you.
Metric system is a French plot.
Hey, don't talk bad about the French. One of our lurkers out there is a French person I know.
Wow.
Hello there, Roxy. Roxy's out there. She's from New York.
One of the results of what they call it, age of reason or whatever. They thought they were going to be scientific with everything, and they said there were 10 months in the year, and the whole basis for the metric system is the meter, which is 39.37 inches.
Yeah.
And they came up with that number, measured from the North Pole to the equator along a line of longitude, and 1/10,000th of that was a meter.
Yeah.
And what they didn't tell you was that's measured along the line of latitude that runs through Paris, France. Earth is not a perfect sphere, therefore the length of each line of longitude is different. They just happened to pick the one that runs through Paris. Actually, a small town with an observatory near Paris. So there. Like I said, it's a French plot.
A French plot. That's funny. Okay, we are well focused here using our French plot units of measure. Yeah. Okay. And to our friend Roxy out in New York, I want to just say, who is French? I just want to say that Daryl doesn't mean it. You don't have to hurt him.
Oh. I kid. Sorry.
It's okay. As far as I know, she doesn't hold grudges. She just eliminates everybody who gets in her way. All right. This will be a 25-second shot of this Crab Nebula. This is a supernova remnant. I think it's 6,000 light years away.
Something like that.
Yeah, I think. Yeah, I'm going from memory on this. So I'm gonna go into from our low light mode here. I'm gonna go into deep sky mode. So we're gonna come out and we're gonna go into live stacking mode, and you'll see the remnant of the Hyades left here. There they are, and they'll stay there until the next picture comes in. You'll see this first image of the Crab Nebula now. And it's really beautiful. Oh, look at that. Yeah. Alright. So what we're going to do, first of all, is bring down our full width half maximum filter to just about there. And then we're going to go back and color correct the image and start acquiring good images. It's already doing so. That's the actual color of the Crab Nebula. It's really something. And this color you're seeing is characteristic of the excited gas that's being given off by this supernova explosion. When the star disrupted itself and spread out into space in all directions, right? Different processes govern how far it goes, because ideally you'd see a spherical thing expanding into space. But the interstellar medium isn't devoid of matter. There's matter there. And so as the material is expanding, that's physical material. It's atoms of actual material, of gas and stuff that is blasting off this remains of the star. it hits other stuff out there. And when it hits other stuff as it's traveling out there, it's heated up tremendously, sometimes into the millions of degrees. However, in the center here, that little tiny white dot you see right there, okay, and I can actually just kind of show it to you a little bit more clarity just by doing this. Put a little box around it. That box is come on now. There you go. That box is circling, or is showing you that white dot in the middle. I'll zoom in a little more as well in a sec. That white dot is the remnant of the stellar core. All right, that's all that's left of the star, 6,000 light years away or so. And that tiny object is literally about 11 to 17 miles across. But we're seeing it from 6,000 light years away because it's so hot. It's giving off so much light, and much of it is in the ultraviolet range, the range where you get suntan from. And if you were anywhere near the Crab Nebula, you would be literally ultraviolet radiated into cinders in a very, very short order. You might not even feel it. It would be so fast. And so that's what happens in the region of these supernovae remnants, especially when we're talking about a star like this. This is a neutron star that has hot spots on it, and those hot spots, they're very hot, such that when it's rotating very rapidly, and sometimes we get hit with this lighthouse flash of this hot spot as it goes by. So it's like as it circles, and that happens in this particular star, which is called a pulsar, because it pulses this energy at us from these lighthouse beacons, and that happens every 33 times per second actually for this guy. But it's not the fastest. For an object that's like 11 to 17 miles in diameter, okay, that's like Manhattan Island. Okay, imagine that as a diameter, and it's spinning 33 times per second. That's huge. Why doesn't it fly apart? Well, because of tremendous gravity. And the other objects that are out there dwarf the speed of this one. There are pulsars out there that literally rotate and revolve on their axis like 715 or so times per second. Imagine something the size of Manhattan Island spinning that fast. You don't talk about it in terms of revolutions per minute. You talk about it at frequency. It's a frequency, and that's amazing to see this here, because this is in fact one of those most amazing things we've discovered in the world of astronomy. When it hit the news, when the first pulsars were discovered, these were just unknown at the time. And if you think about it, now the thing that's amazing to everybody is the fast radio burst. And these are, again, the result of neutron stars, but very special neutron stars that have extremely high magnetic fields that would literally tear your atoms apart in your body. And those are called magnetars, like magnet and then tar, magnetar. And magnetars have such an incredible magnetic field, they can generate pulses that send energy to us that lasts but a few milliseconds. And that energy is so powerful that we can hear it, so to speak. We can see it arriving at our sensors from billions of light years away, where they occur in very, very distant galaxies that we can't even see with our telescope here. So there's a lot going on out there that we just don't know. I'm going to sharpen this up here, so watch the filaments now.
Imagine you took a star, it was originally much bigger than the sun, but what's left of it is probably comparable to the size of the sun or a little bigger. Chandrasekhar's limit, I assume, 1.4 masses. And you crush that thing down till it's 8 or 11 or 17 miles across, but it still has all the mass of the sun inside it. And like when a figure skater pirouettes, which she pulls her arms in to spin faster. When the neutron star collapsed, that same idea, centrifugal force, it sped up the star, which is why it's spinning so fast.
Yeah, angular momentum.
Yes.
So the thing about this mass, when we look at a planetary nebula like the Dumbbell Nebula in the summer sky of Vulpecula, and we look at, say, the Helix Nebula in Aquarius, the central star there is not a neutron star. That's a different type of star death. That's for stars more like our sun, and that star death leads to an end state called a white dwarf. Now, white dwarfs are, again, very, very compact items. If you took a spoonful of a white dwarf, let's say a sugar cube of white dwarf, and you measured it here on the Earth, it would weigh about 200 cars, okay, in weight, okay, 200 vehicles, standard vehicles, okay. If you took a spoonful of this star that we're looking at right here, this neutron star, now you're talking about 262 million tons of material. All right, 262 million, 262 million cars. Okay, it's really astronomical how much it goes up when you get to bigger mass stars. And you got to understand that they rotate very quickly, and you say, well, how come they're not flying apart? Well, they're so compact, they crush down so small, they have a tremendous amount of gravity, and slightly higher, and they'll become a black hole. And then, of course, it bends space, and light can't even get out at that point. So we're talking about this exponential increase in this this gravitational gradient. And it's really incredible. And so when we look at white dwarfs versus like the Helix and like the Dumbbell and like our sun will be eventually, and then we look at neutron stars, we're looking at an exponential difference in both how they're made and how they hold themselves up, okay, and how big they are. A white dwarf's about the size of the Earth. A neutron star like this guy is about the size of Manhattan Island. The difference is astonishing.
Yep.
Yeah.
And the only thing more extreme than a neutron star is a black hole.
Yeah, and that we can't see.
Yeah.
Well,
and I mean, this is about as big and bad as it gets, and still sort of be here.
yeah.
You could say by the time it hits a black hole, I mean, it's not really here anymore.
I guess that's true. I guess that's kind of true, isn't it? All right, so I'm going to take us down to the low end here, and I'm going to move this mid-level, leave the black level where it is, and take this down to try and show you the core. Okay, now look inside, and you can see all this filamentary structure. This stuff in here, and there's that neutron star right in the middle. You'll notice it's got all kinds of filaments. Now, what is governing the generation and structure of those filamentary structures? Shouldn't it just be mass all moving out in all directions? You might think that, but there's one thing that you're forgetting possibly about what's going on in addition. When this star first explodes and starts moving this stuff out, okay, you have to keep in mind that at that point, it's not expanding as a vacuum. It's expanding as a mass of material. And not just a mass of material, a mass of charged material. So we have lots of protons, we have lots of electrons, and protons are all positive one charge, and electrons are all negative one charge in our standards. And so we have charged material. And charged material moving outward with other charged particles and electrons tend to interact with each other. So there's probably a tremendous amount of interaction between these protons and these electrons in this expanding debris of star death that we're looking at. And those spindle clouds are probably partially created by the charges interacting with each other. Not only that, yes, it's not an even interstellar medium that it's expanding into. Clearly, there's knots of material here and there, and if the material encounters it, well, then this might happen. It might leave it might be able to push through. It might not be able to push through, and it goes around it or something. I mean, we could look at that as something that defines the overall shape of the Crab Nebula and other supernovae. Okay, there are some planetary nebulae, which of course are smaller in size and take up less light years in diameter, about 2 to 3 light years in diameter overall, as far as we've seen. But these guys can be many light years across. Okay, the Spaghetti Nebula that we looked at one point, ancient supernova. Okay, Barnard's Loop in Orion, the remnant of an ancient supernova, massive arc of material. All right, and the way they look is all spread out, all disheveled, because they've had many hundreds of millions of years to expand not this particular supernova, but to expand and interact with the interstellar medium. Okay, this supernova occurred in 1059 AD. 1054, sorry. That's right, 1054 AD, and the Chinese astronomers saw it, and they saw it during the daytime because it was bright enough to see in the sky, which is hopefully what you'll get to see when Betelgeuse goes supernova, and let's hope it goes sometime in the next couple of years. And then you'll see a new star in the sky joining the sun, but it'll be a lot fainter. It'll probably be somewhat brighter than Venus and much, much dimmer than the sun. And it'll be really cool, and you'll see that like that in our daytime sky, if Orion's in the daytime sky, for at least a few months maybe. And so I think at that point, if you consider the fact that that's a 700 light year distant, more or less, star, number one, we have nothing to fear from it, but we can just enjoy the fireworks. And in the months following the dimming of Betelgeuse, the first images of Betelgeuse and its environment will be shown, and we will see the expanding cloud of debris, much like we did with supernova 1987A, which was an incredible supernova in the southern hemisphere that I didn't get to see, of course. But still, there was a lot of study done of it, and one of the things that happens is the supernova occurred in a cloud of gas, and when it occurred, there was what's called a light echo. You literally saw the radial pulse of light moving out.
Yep.
And that was the most incredible thing. And they got that on video. They just kept taking images of it. And over time, you saw this thing moving out. Same here. We don't see light echoes. We see the physical movement of this material. We actually watch the Crab Nebula expanding from the supernova site over the last 100 years. But see, we don't have a long lifespan, right, guys? So we're constrained to just watching from a long distance and as slow as it takes. The universe has time aplenty. Hey,
when
Blues
we
Traveler.
see this, we've seen the Veil Nebula many times.
Yeah.
If you remember how mixed up and turbulent looking it is, this is the same thing going on here, just farther away.
Yeah.
So it looks smaller, but it's really, is it bigger, smaller? Really, I don't know offhand. The Veil Nebula is closer to us than the Crab is, if I remember correctly. So
Yeah, Veil's
it's much bigger
1,600 light years away.
and the Veil is bigger than, I think, several moons in the sky.
Yes, it is. I think
the
4
whole
or
thing.
5.
But we're seeing the same end result here.
Yep.
That's where all the filaments come from. It's a big bada boom is what it is.
Yeah. An amazing explosion, a cataclysm. And you know what? We used to think it was the worst possible thing that could happen in the universe. Now we know it's not true. Because there's 2 types of nova. This is a supernova. Okay, there's a regular nova, which is far less of a problem. Then there is a kilonova and a hypernova. Now, I wish I could show you a kilonova and a hypernova, but I can't because there's none within our view. But those are other types of novae that have been discovered. A nova is interesting, which is different than this. A nova is something that can actually recur, and usually it requires a red giant star to have a companion star that's already evolved to a white dwarf. And when Daryl mentioned the Chandrasekhar limit earlier, that 1.44 solar masses, that's the size, the mass that a white dwarf can be before it becomes unstable. Anything bigger than that, and several things can happen. There's research indicating that maybe they could continue to collapse into a neutron star under certain conditions, but in all likelihood, they can also literally destroy themselves in what's known as a type 1A, that's Roman numeral 1 and then the letter A, supernova explosion. And they're remarkably similar, and we've learned that they're identical in their output wherever we see them. So if we see one in a distant galaxy, which we can tell by its spectrum, we can tell the distance to the galaxy very accurately because we know how bright it is in our telescope, how bright it should be if it was a certain distance away. That's called the absolute magnitude, and thus from those we can get what's called its distance modulus and calculate the distance to the galaxy with some accuracy. It's pretty cool, you know. But you know, the other type of nova that we see is one like our T Corona Borealis. We were watching it for quite a while. We've got lots of images of it. We never actually caught the nova because it seemed to happen at a point that surprised everybody. But T Corona, when it went, what happens there is, again, it's a red giant with a companion star, and that 1.44 solar mass limit was never reached. But what happens is the red giant gets bigger and bigger and bigger, and it starts leaking hydrogen onto the surface of the white dwarf. Now, that's mass. And if that mass were to exceed 1.44 solar masses, then what happens is that the star goes into a runaway fusion on the surface and blows up the star, and that becomes one of these type 1A supernovae. Okay? That's when you have more than that magic number of mass on that white dwarf. However,
well, it doesn't actually blow up the star.
Well, a type 1A supernova, will cause a star to blow up.
Well,
but a nova won't.
I meant the nova.
Yeah. So
T Corona, it happens about every 80 years.
Yes, and that's what I'm describing is how that process works, and you know too, I think, but for folks that don't, if that white dwarf doesn't have 1.4 solar masses, let's say it's only 1.1, and adding hydrogen to its surface only brings it to 1.2, 1.3. Now that hydrogen on the surface can spontaneously fuse without danger of destroying the star. And you won't get a type 1A supernova like we're talking about. You'll just get what's called a nova. That fusion brightens up the system of the red giant and the white dwarf exceedingly brightly for several days, maybe a week. And then it fades away. And then it goes and continues to feed hydrogen again, and it goes through this all over again until the red giant phase of the other star is done. So then in the end, you might have two white dwarfs orbiting each other. So that's kind of how the nova, supernova process works, and you know the white dwarf versus the neutron star. Stellar evolution is really fantastic, and I've said this before. For one of our projects we had to do in astronomy, we actually had to build a star, and we used a book called Stellar Atmospheres by Ivan Novotny. It was a very, very good book, and it talked about all the mechanics and physics that goes on from the core of the star on outward. And stars are exceedingly complex. They're not just big balls of hot gas and doing fusion in the core. There's a lot more going on in the star, and we had to account for it. And the star I built was stable. I had reached what's called hydrostatic equilibrium, so that the pressure of radiation pushing outward was equaling the pull of gravity trying to collapse it. So it stayed, like a balloon where you pinch off the nozzle. The pressure outward equals the pressure inward, from outside, and so it could hold itself up. And many times my star would collapse and go into a uncontrollable disassembly. Okay, but once we figured it out, it worked. So it was very complex to actually engineer how stars work. But once you realize it, it's something that sticks with you for a long time. I think in the back room here, in a steamer trunk, I actually have the printed out program that I wrote for the star. It was months of work, and it was like pages and pages and pages. But stars seem so simple, but there's so much complexity. And different stars, a slight difference in temperature, like 1,000 Kelvin. Kelvin is a temperature unit, so you could have 0 as absolute 0. It starts at 0. A difference of 1,000 Kelvin could mean the difference between seeing a circulation of like a pot boiling, okay, which is a convection cell, versus a radiative pressure pushing outward from the inside. So all kinds of stuff there. Neato. And here's Lubo. Hi, Lubo and Goblin. All right, I'm done talking for a moment, so you can continue. I'm just letting the rest come in. We got 51 shots here.
I might continue on something I think you started on a while ago.
Yeah, go right ahead.
You mentioned kilonovas and hypernovas.
Yeah.
An event happened 2 or 3 years ago. They said it was the biggest boom ever, the brightest thing ever. Something exploded in a galaxy billions of light years away, and it was detected here on Earth. And the magnitude of this thing was such that it had, even billions of light years away, it had noticeable effects on Earth's upper atmosphere.
Oh, you told me that, yeah.
So they could measure that. And it was like the biggest boom we've ever seen. And maybe that was a hypernova.
Yeah, I think so. And there's a product called Space Engine that I use to do three-dimensional, voyages through the universe sometimes in the streams. And it has that hypernova in it. And it's labeled a hypernova, so you're right about that. Hey, Kate Lawler, nice to see you. Hey, look at Roxana, she's here. This is a different Roxana. This is Roxana from Indiana, I think. Not New York. Yeah. She has this great Facebook group called Starlight. Lubo is saying he's having some bad weather coming in. Hey, and I hope you actually get to it. Cosmic Ray asked what happened to the Blaze Star. It's suspiciously thought to have gone nova on us, but it acted very differently. Apparently, it seems to have actually already done its thing, and really? As much as we tried to catch it, it didn't happen while we were watching it.
I had wondered a while back, elsewhere on the web, people were wondering, when's T-Core board going to happen?
Yeah.
And I mentioned that, it was, people were thinking it might have happened, or was going to happen last September.
Yeah.
And it never did. And because of all the stars slowly dropping into the sunset over the course of the seasons, Corona Borealis vanished into the sunset.
Yes, it did.
And it was hidden for several weeks. And then it popped back up in the morning sky, as stars tend to do. there it might have happened while Corona Borealis was hidden in the sun.
Yeah. Or it might have waited till the morning because it knew I wouldn't be up that early. Yeah. Okay, so we're going to save this one more time. Last one we'll do is 60 exposures. If you want to find any of this stuff, you can go to skytourlive.org and scroll down and say, take me to some cool pictures and read there, and it'll tell you how to get to these. And this picture you see right here, okay, when I save it, which I'll save this one right at that goes to 60. Okay, all right, and there it is. So I'll save it now. And I'm saving the astronomical FITS file format, which looks black with a couple of stars to you. It won't look really good. But then I'm going to save it exactly as seen. And this is the image that you will get if you go up there. You can take down both. Okay, let me just grab it for you here. Let's see, 183, 2024. Yeah, this must, no, is that it? Might not be it. Yeah, that's it. And this is the image you'll get. This is the Crab Nebula and its environment around it. And you got that beautiful blue neutron star pulsar in the center. And you can take this for free. This is yours. Okay? And it'll be up there for the taking. Everything we take pictures of is available to you up there. And Daryl put the link up. Izabela did it earlier. Very nice. Thank you both. And now we're going to come out of this and we're going to go to our low light mode again, and we'll check out something else. All right, so I didn't see any other faint objects in that field, so I don't think the comet was in there, but I think it's pretty faint. Doesn't mean we can't see it, it's just that we have to look for it, I think. Okay. Hey, Fantasy. Nice to see you, man. All right, so let's check out. Let's come down here. We'll check this guy out. Daryl talked about Gemini earlier. So let's dip down a bit and just head there for a moment. You can see the telescope moving just slightly. And you'll notice also that when we come here, okay, this is this beautiful cluster. Now, did you see the Hyades when we took that picture? Bright stars, like just sort of making very bright spots here and there, just very much so. Look at these here. If we got closer, if we were closer to this cluster like this, okay, well, you see how we could be in this cluster and see at some point we're going to see a sky kind of like we saw with the Hyades. But these have many more members in it. Okay, this is all live, by the way. All right, and there's another cluster over here that's much further away. I keep forgetting, is it 2153, 21? Let me see. NGC 2153 or something, like 2175. No, 21. I'll get it. There's a reason I'm going for that, because I'm trying to show you something here. And we're going to come down here to this.
2158.
Yes, thank you. 2158. So this is Messier 35, and Charles Messier captured some of the brighter objects, and then the fainter objects he either didn't catalog or didn't see. And this is a new general catalog NGC object. This is 2158, as Daryl just said. It's much further away, and if you notice, the stars are a little more yellow. It's because it's far away, and we're looking at it through a lot of dust. And starlight is reddened. Okay, it's called interstellar reddening, and starlight is reddened by this dust, and that's why it looks a little bit redder and fainter. They aren't redder and fainter stars, usually. It means that they're just seen through dust, and the dust scatters the blue light. All right, just like our molecules scatter the blue light from our sun, giving us a blue sky. Sunsets are red because more blue light is taken out of the sunlight. Same here, more blue light is taken out of this distant cluster by the dust between us and that cluster. Okay, we're going to make this a 15-second exposure. take just a few of these, and then we'll move to a beautiful nebula that's right down below this. All right, so this, we'll stack this. You'll see the last Crab Nebula stack here, and then it'll go away as soon as the new one comes in. It's not being lost. It's already saved to the server. But look at that. This is Measure 35 in Gemini, and I'm going to back the black level off the peak just to the left so we get the maximum starlight. Okay. And you can see this cluster here is more red. And it's because it's more distant. And I'm going to also color correct the curves here. All right. And that helps us. All right. And now, if I just come down here and take this mid-level and bring that back a little bit, just enough, we can start to see some of the detail in here. There you go. Look at that. So you've got this beautiful, almost yellowy cluster, and you got this gorgeous cluster here that has mostly younger blue stars in it, but they are evolving quickly because you can see that there's some red ones in here. These are most likely red giants, because even though this cluster is still cohesive and staying together, it doesn't mean that they're young hot stars. It can mean that they're massive, more massive stars, and they evolve quicker. So they might measure their lives in, say, a few tens of millions of years, several hundreds of millions of years, and like the stars in the belt of Orion, O-type stars are hot and blue. They live their life very short. The brightest candles are the shortest lived. And so these stars here have evolved most likely in this cluster. But this is a beautiful comparison here, seeing them both there. Right, and this is our annotation, so you can see, and we'll save the image with the annotations. Well, I saved it to the wrong place. My mistake. Okay, I'll have to set the target name, go through the complaint. Yep. Go through the complaint. And then I can save it to the right place. And now it saves it to the right place. Okay. And then if I save it within here, we get the image with these annotations on it. If I save it here, whether we had that up or not, we would get the straightforward image here like we have here. This is a beautiful one. All right, so that's what we're going to do. Just 10. Don't need to do much more. But it just shows us all this amazing structure of the universe. And it's not just two star clusters. It's a very distant cluster seen through dust that's causing it to be reddened. And that reddening is the thing that is, well, it's a bane of astronomers. We hate that because we have to calculate how much the reddening is. We have to calculate how much stuff is between us and there. We have to look at other clusters like this one, figure out if this one is near this one's age, and decide that based on looking at this one, its stars here are probably going to be like its stars here, and we can actually do a comparison that way and figure out a lot of details about it. But it's hard.
Can you zoom in on 5128 a bit?
2158, sure. That's pretty.
Yeah.
Yeah, it's high in the sky, so we got some good detail, huh?
Yeah. I was just curious. Before you zoomed in, I mean, you can still see it, but it looked like there was a line of bright stars across the middle of it.
Oh, here?
Yeah, running left to right, pretty much across the middle.
Okay, if we back out, maybe we see it. Kind of like this here.
Left to right.
Well, left, right, yeah. You mean this way? Like straight left, right?
Yes.
Okay, I see that too. Neat. All right, well that's what I wanted to do. That just get a brief shot of that, and let's go back to our low light mode so we can actually view some of these new objects. We're going to go down now to a gorgeous nebula that I've never taken a picture of with this camera, and it's right near here. It's this guy right here. We can also do the jellyfish, which is right here. But we're going to go down to this one. This one's called the Horsehead Nebula. The Horsehead Nebula. We've never done it with this camera, so I'm looking forward to it.
I think you have.
No. Not with this camera.
Okay.
Yeah, I haven't. Yeah. Okay, so it's right here. You can kind of see it. Well placed. Focus should be good. So let's give it a 25-second shot. We can go a lot longer than that, guys, but 25 seconds is all this telescope needs. With the new scope, we'll be taking shots a lot longer, I would imagine. Not always, though. Karen Belmont says, never heard of the Horsehead Nebula. I know you haven't. Now you will. Okay, so we'll see the Crab Nebula, I think, when I pull this up. As our it's last, measure 35 and 2158. And this is, in our buffer. So it's saved up to the database. It's already up there. But here comes 2158. Oh, look at that. Here's 2158. Let's back out a little bit. Let's color correct. Let's make sure our full width half maximum. Yep, we're good. And go back here. And let's move this in. Richen our colors a little bit. Now, this is really neat because it's a cluster in here that has started to excavate a cavity around itself. That's what happens when you see hot young stars are formed. They create a cavity around themselves. The Rosette Nebula, for instance, which is actually right nearby. That does that as well. Those stars do. And we could probably look at the Rosette as well. But if you notice around this edge right here, look at these structures here. These are this is areas of dust, but you don't see all this complex knotty K-N-O-T-T-Y dust in here. Why is that? It's because the stars in here have excavated that area clear, and where it's denser, it doesn't go so easily, and it kind of leaves itself behind. We may be looking literally deep inside the nebula here, and this could be an outer wall. We could be looking down like a tunnel, but this is all dust around this here. This is all black dust, and this is an area of excited hydrogen created by the hot stars in here. Let's blacken it up a little more, Daryl. Maybe go right to just to the left of the peak. Yeah, there we go.
Nice.
That looks nice. And now let's color correct again. We color correct routinely as we take our images.
Monkey looks like it's got a bad attitude.
No kidding, huh? It's mad.
Looks like he's on fire.
Well, that's why he's got a bad attitude.
Well, I see his mouth. I see his ear over on the left. I see his eye above his mouth. And he's got a little pushed-in nose.
Yeah.
Interesting, up at the top right, there's that particularly red area. What could be going on right in that immediate area?
Or this.
Just more concentrated. Yeah.
A higher density of hydrogen in there is undoubtedly what's happening in there. If we go way down, then you can kind of see there's some more, like in here.
Yeah.
And there's more here. There's stuff here. This area is right near a star, and the star is probably embedded in here. This color here is probably a combination of excited hydrogen and possibly dust that is scattering the blue light of the stars inside. And I don't know the proportion of which in this particular nebula. But we'll come back to this now. Now this, I'm going to overprocess. This guy over here, I overprocess using this just to get an idea what else is in here. So we'll back out. And now let me just overprocess and see kind of what's hiding back there. Okay, so we almost have everything for this particular nebula. There is a really interesting reflection nebula, emission nebula focused on the bunch of stars right here. I suspect that those stars are the ones causing it. Right there. So that's kind of interesting. It's actually not just kind of interesting. It's really interesting. Because life began in the dark. So in this dark material in here, you have protection from the hot ultraviolet energy of these central stars. And that protection allows your clouds to get very cold and allows you to get a contraction of material, a condensation of material that will collapse gravitationally on itself and not be driven away by hot ultraviolet energies because the cloud is protecting it. So we get that. Now look at this interesting area right here. Okay, there is a interesting reflectivity going on here, and it kind of merges with some dark nebula here. Okay, and some hydrogen being excited out here. Really neat stuff. Let's see if we can push this and see what's hiding in there. Yeah, it is a fairly well-defined nebula. And I'll go out to just where the noise goes away. Okay, right about there. We have 13 shots that we've captured so far. The reason we take more than one shot is because if you look close up here, like if we just zoom in on one section, do you see this blotchiness in here? That's digital noise generated by the chip, the sensor that's capturing the data on this camera. All right, and that data that's being captured is going to, let me just get rid of that right there. The data that's being captured is data's being captured is going to produce an image, right? So we take one image, take a second image, line it up with the first one, and stack it on top, and we make an image sandwich. And we keep doing that. We pile them on top of each other, and as you see right there, we've stacked about 15 different ones already. Like right there, you can see 15, and now 16. So the more we stack, the better it's going to look.
I don't like that monkey's look.
Yeah, Bad Monkey. That's a production company, Bad Monkey.
I think I did that.
Yeah. Izabela's talking about, and you responded to it. They're thinking of declassifying the JFK and MLK files.
Yeah. That'll probably devolve into politics.
Of course it will. Of course it will.
If you want to go there.
Yeah.
I think you can tell when you look at that, especially on the right side.
Uh-huh.
All the black you see, folks. That's not nothing. That's dark clouds.
Yeah.
That the monkey head is actually buried in a big dark cloud.
That's right, a molecular cloud. That's you can see this black material here. That's up here in the foreground, and the bright stuff is being blocked by it, behind it. You can just imagine that. That's what's actually happening in the universe everywhere. When we look at the Rosette Nebula tonight, you'll see that especially ring true. It's very obvious. Wow, this is really pretty. Well, let's get our target name now. Yeah, Monkeyhead Nebula. We'll do that and give it our target name. Save the image with annotations. Alright, been saved. Then we can come out of here and save 20 images stacked here. And then save them exactly as seen. So that means we do this. This is the image that's up there now for you. It'll be up there in about 30 seconds. Where is it? SkyTourLive.org. You can go up there. You can click donate if you like what we do. You can join our Patreon if you like what I do. You know what we do. You can go to our Etsy store up there and see images like this emblazoned on mugs, t-shirts, sneakers, and all kinds of things up there. Blankets. We've got like 50 or so products up there now. Water bottles of all kinds. Daryl has a Pleiades mug and he likes it a lot. Hopefully it's still intact.
It is.
Excellent. I dropped one of mine, that's why I'm saying that. I felt like I was...
Don't blame me.
Oh, no, I know. I felt like I was punching a friend in the face when I dropped that mug. I was like, gosh, I can't believe I did that.
Well, the mug I have,
It's big.
it actually holds 2 cups of coffee. It's a big, tall mug. And I thought I would retire my old 1-cup mug.
Nice.
I find that I use the big mug in the morning and the little mug in the afternoon.
Excellent.
And I put my tea in the little mug too.
Very good. Yeah. Well, this we're gonna go to 25 images, then we're gonna save it and move on. Look at these beautiful nuanced areas. These are just incredible. You're looking at 3D structure, remember. They're not just sticking out, they're curling in or out and it going every which way. And that's something that's driven by the forces there that are moving this material around. Usually, the ultraviolet energy that's being emanated by these stars.
If you look between the monkey's mouth and its eye, I guess you would say, there's a pillar in there.
Are you looking here, you mean?
Below that, just below that. Skinny little black right there.
Okay, that guy.
Yeah. That's a pillar, just like what we see in the Rosette or in the Eagle Nebula. Pillars of creation.
Yeah, it's actually...
You see it's pointing toward those stars up above it.
Yeah, it is in part being affected by them, no doubt about it, huh? But see, that the pillars we're talking about, they're actually not as obvious in this nebula because the stars in here aren't of the immensity and mass to generate a lot of energy. I muted so I could sneeze, guys. Sorry. Okay, so 28. We'll just save it here. This is good. The Monkeyhead Nebula, ladies and gentlemen, boys and girls. All right.
I don't want to get into politics or all this, but things seem to be coming hot and heavy lately. And Bill, New York Skywatcher. There was supposedly some huge news about UFOs or UAPs coming out like last week, and then the story broke, and it was that stupid egg-shaped UAP under a helicopter, whatever that rope was. And
I was asked to analyze that.
Yeah, he sounded very let down.
Well, okay, that for those of you that have seen the video, you know what I'm talking about. For those that didn't, you're going, huh? What's that? A video came out by Ross Coulthart on News Nation, put it out. He received it from a so-called whistleblower, and it shows a helicopter with an egg-shaped craft in a cargo net and being lowered down to the ground, supposedly in a night vision green view. Well, you know, I have a team called the photo analysis team with MUFON, all right, and we have 6 or so people, and we all looked at it and came to our own conclusions, and all of us together deemed it a hoax. And my reasons were numerous, okay. Among them, it looked like it was definitely a fake night vision shot, you know, a daytime shot that was put with a green filter to kind of look like night vision. It was being set down in a field. There were no personnel around it, nothing. If it was a real UAP, you wouldn't just stick it and set it down in a field, okay. So those two things. The next thing is you're hearing the sound of the helicopter, you know, up, you know, while the video's going on. Guess what? Those technical down-looking cameras don't even have sound. That's not what they capture, because they'd be totally overwhelmed by the noise. The sound inside the helicopter and around the helicopter is so loud that it would be like white noise to a camera microphone. So that's not at all right. So those 3 things alone made me really think that this was probably a hoax, and I don't think I was wrong about that, unfortunately. I just don't. So there was a number of more reasons I gave, but you know, it just was not the disclosure that we were waiting for.
Oh, Bill was really bent out of shape.
Yeah, he probably saw my report. Okay, this is Propus. It's a star. I gotta look and see. I think it's a red giant. It is. It's an M23, Roman numeral 3. M2 meaning low temperature. O is hottest. M is the coolest. So we got O, B, A, F, G, K, M. You know, or O, be a fine girl or guy, kiss me kind of a thing. That's a mnemonic to remember it. O, B, A, F, G, K, M. O's are hottest and bluest. M's are coolest and reddest. And so this star is cool, but it's giant, because the second element is what's called a luminosity class. All right. If it's a Roman numeral V, like 5, then that's like the sun. It's called a dwarf. If it's a Roman numeral 1 or 2 or 2A or 1A, then we're talking about a supergiant. And a giant star is like a 3, and this is a Roman numeral 3 star. So it's a big red giant star. And its actual distance from us is about 350 light years from us. So that's this star here. And I'm going to move Propus to the east a little bit, because hiding in here is a supernova remnant, like the Crab Nebula we looked at, except it's more distended. And you can kind of already see it here. You can see the beginnings of it here. And I'll move down a little bit, just a little bit. And I think this will be perfect right here. Okay, and again, this is, you can see a filament already here. Okay, I've never taken an image of this either with this camera. This is the new camera that we've added. We'll do a 25-second shot as well. And I'm going to drop us down to 250 on our settings here, because we don't need to go higher than that. All right, so let's come out of that mode, low light mode, and go into our stack mode. We'll see the last image in the buffer, the monkey head, and that's up on the server. Been there for about 3 or 4 minutes already, maybe 5 minutes. And so it'll be replaced by this image coming in here, at least on our screen here, not on the server. And this is the Jellyfish Nebula that we're going to look at now. Let me go to the histogram. Let's color correct. And now let's bring in the detail. Boom. Here we go.
Did the process change somehow? Or was there an update on your sharp cap or something? You seem to be taking different steps than you used to.
Oh,
going from one image to the next.
Oh, I discovered a few shortcuts, you know,
Okay.
and so I've been using them, like leaving the image in the buffer. I don't have to clear it; it'll overwrite.
Yeah.
Little things like that, which you've noticed. So
Yeah.
this is the Jellyfish Nebula. Now, one of the things that's interesting about this is the progenitor star that created this. You would expect to be in the center here, but it's actually down here. I can't remember which one it is. It's one of these stars, and the whole point is, how could the star be missing from the center of the explosion? Like in the Crab Nebula, it's right in the middle. In the Helix Planetary Nebula, it's right in the middle, the white dwarf, right? So where is it? Why is it down here? It's down here because the star was already moving fairly rapidly, but during its supernova, it was irregular in its explosive force. Note so much more over here. And so it propelled the star, in addition to its motion through space already, in a direction that took it down here. I think it's one of these stars, actually, right in here. I had done this before and actually did an article on it and showed it exactly where it is and talked about the motion of the star, which we call the proper motion. But this is the Jellyfish Nebula, and let's see what this thinks of it here. Yeah, supernova remnant. It's in Gemini, and this is Eta Geminorum. That's the name of this star here, that Propus. Okay, I'll save the image with the annotations. Oh, I did it again, didn't I? I have to set the target name first. Okay, and then save it, and that's gonna complain, and then I'll say yes. So then I'll save it again, and it'll go to the right place. So instead of monkey head, that'll change. There we go. All right, so this is cool, and we can get rid of this for now because that image is out there. You can go actually look at it, and you'll see this. You'll get the image with the annotation, so you know exactly what you're looking at if you want to check it out, what we talked about in tonight's astronomy class. Speaking of astronomy class, I had a wonderful meeting today with the people at Aquila's Nest Vineyards, and they have this remarkable thing that they do. They name all their wines after astronomical objects and astronomical events. So I saw that, and I called them and said, hey, would you guys be interested in astronomy talks and a sky watch? And they're like, yes. Wow. So I went down there today, and they're actually going to open up on a day they're not even open, just so that we can have this special event, and we'll do like a bunch of them if we can, over time. So if you're in Connecticut, you want to look at the Aquila's Nest Vineyards events in March, because they want to start right away in March. And I'm probably going to do an inside talk for March with maybe an outdoor sky watch if it's not too cold outside. But it'll be a very enjoyable night. I'll have a great time. They're really good people. And I think the cost is going to be like $10 admission or something. So you can't beat it, right? And I'll also talk about UAPs and UFOs as well. Wine in space, Roxana says. Yeah.
Aquila's Nest?
Yes.
Eagle's Nest.
You got it. Yeah. It's in Connecticut. They have a beautiful hilltop, beautiful hilltop vineyard. By the way, Roxy in New York, by the way, says that she forgives you for insulting the French.
That's not Roxanne in Norvège?
No, a different one.
No, I don't see her.
Yeah, she didn't post anything in here.
Oh.
She sent me a message in the chat on my phone.
All right.
Okay, let's do that. And now let's... Oh, this is beautiful. Watch this. Now as I pull this in, you'll see more filamentary structure avail itself. Look at this delicate filament right here. Okay, this kind of thing that you're looking at right here, again, this could very well be due to electrical charges in the locally dense medium of this expanding superheated cloud. Yeah, it's Roxanne. It just is. Es un cubano. So, I think that's pretty cool. Let's actually, let me get rid of this. And let me move this over. And allow us to see all of this. That's cool.
This is the jellyfish, right?
Yes, sir.
Is this in Stellarium?
Let's go look. I believe it is.
Well, what I'm curious about is if Stellarium will tell us how far away the jellyfish is versus how far away that star is.
Oh, you're talking about Propus.
Yeah.
Okay.
What's the distance to Propus?
Well, we mentioned that earlier. It's about 350 light years.
Okay.
And I think Propus is a foreground object to this, but
yeah.
Let's do this. Let's bring up the Deep Sky Object Database here. Let's bring up the Sharpless catalog, Vandenberg, Lynn's Dark Nebula, Lynn's Bright Nebula, Melamed we won't do, that's clusters. But this is supernova remnants, and that might have it in here. Let's see if that has it in there.
I was just thinking, sitting there looking at it, that if you didn't know any better, somebody might think, because the colors are similar, that Propus might be what's exciting the jellyfish, and I know that's not the case.
Yeah, no, you're right, obviously.
As you said, I assume Propus is a foreground object.
Okay, yeah, see, it's in the supernova catalog.
Okay.
Yeah. It's SNR Green. Green is the cataloger guy. He did the catalog. Green 189.1. And here's what it is. These are the coordinates. All right? And the declination. So that's how this works. They give it, it's like the Bonner-Dirk-Merstring. Okay? They actually give like a coordinate system, but it's not in right ascension and declination, which is really confusing. So
does it give a distance?
Yeah, the distance. I don't see the distance. I don't think Green did the distance calculations. You should look that up. Look up SNR G189. That'll probably give it to you. Or just look up Jellyfish Nebula distance. I'm sure it'll tell you. Let's go back to the Jellyfish in progress. Rejoin this in this show in progress. Very fine details here. These details were inaccessible to us with the previous camera. Look at this. Wow, look at that beautiful area. There's a local density here that's glowing. And this is not where the progenitor star is. The progenitor star, as I said, is down here.
Okay. Propus was 300 some odd light years away.
350, yeah, 349,
Okay,
plus or minus 3.
This is also known as IC 443 or Sharpless 248. Is 4,892 light years away.
A lot further, yeah.
So it's over 10 times farther away.
Yep. So now, if you guys are wondering how big this is in light years, well, I do have a program, and if I bring it into Photoshop, I can measure it, and I have a calculation built into Photoshop I stuck in there that will give me the immediate size of this thing in arc minutes, and knowing how big it is in arc minutes, I can calculate it with my program to tell you how far it is and how big it is in light years. So now, based on the expansion rate that we see with it, we know that it was expanding slightly faster in the beginning, and now it's slowing down as it goes out because it's hitting stuff. This shape here, this circular shape, is in part due to the fact that it was a spherical explosion. So when you look at this may not be something like this on edge, okay? It might be a half hemisphere of rounded material that's moving out like a bowl. So like this side could be closer to us, this side could be much further away, and it could be a concave bowl of material pushing away from the center of where the star was when it exploded. But it moved way down here, and that's the thing that I thought was interesting. It might be in here. I don't remember where it was.
What, the actual location of the supernova?
Yes.
Looking.
Yeah, it's down. It's below here somewhere. Let me go by. Look at my full width half maximum. Okay, I'm just gotta raise that slightest amount. There we go.
It's about 5,000 light years away, and it happened about 30 or 35,000 years ago.
Yeah. Okay. We've stacked 16 here so far. Yeah, this is gorgeous. Oh, I'm telling you, it's such a beautiful location. I'm going to save this here. Save it exactly as seen. So on the server, this right here, this image right here is going up on the server. It'll be there in about 30 seconds. Roxana, sí, cubana, es la verdad. Yo sé. Yeah, so yeah, I enjoy supernova remnants. It's very, very cool because they represent some of the most violent things that have happened in the universe. But their violence begets life. I mean, it creates these shock waves of material going out that cause local gravitational contractions of dark clouds and other things along the way, which build stars and planets. So supernovae are the death of one star, and they give birth to many stars as a result. And we'll see that in a little bit here.
Mark, could you excuse me a moment, please?
Yes, I excuse you. You are excused. I'm not. There's no excuse for me. So do you like this, guys? Do you think this is cool? You know, I hope you do. It's pretty cool. I will redock this now, and I'm gonna bring back the telescope just to make sure that it's doing what it's doing. Here we go. Thank you. All right. Yeah, so that's really something. We can see on the outer fringes, you can see that little change of color out here too. On the leading edge of this expanding cloud, some things are going on out here, collisions with other material, heating this material to many hundreds of thousands, even millions of degrees. You know, now if we were to zoom into this, now we'll lose it because it'll get lost in the pixels. Okay, but imagine being on the leading edge of this. Okay, if you were here, you probably wouldn't see anything. you would just register a locally higher temperature of material that is in your system. Atom by atom, that temperature will be a little higher because it's being excited by the shock wave of this moving front going out. You might not see it though, because again, this is light years in size. So if you're in here, you wouldn't notice that. Give me a perfect example. We know, and you know from our work we've done, we know that the Pleiades stars are traveling through a dark cloud of gas and dust. That dust we see around the Pleiades stars when we take images, right? So that dust is, of course, something that is we're used to seeing it with the Pleiades, and so we say, oh well, the Pleiades have this dust around them, but they weren't born there. They're just passing through. That's a cluster of about 1,000 stars, not just the Pleiades, the Seven Sisters, but there's 1,000 stars associated with them, and they're drifting through this cloud of black dust particles and illuminating it essentially as we see it. Well, now the research seems to indicate that we too are also in that black cloud of dust that the Pleiades are going through. Maybe we're part of that dust cloud. Now the Pleiades are 400 light years away, and that's nothing in galactic terms, so a dark expansive dust cloud can travel hundreds of light years easily, thousands of light years. We know they do because look at spiral arms in a galaxy. Okay, they go 100,000 light years in size sometimes, these arms of dark dust. So we could be in a dark dust lane easily within the Pleiades dust as well. And therefore that means that everything that we have measured, seen, learned, visualized, captured, computer modeled has been from within a dark cloud of dust that is contaminating our results. So if that's the case, we might be in some serious trouble with our understandings of astronomy and cosmology. Yeah, will that be found out in our lifetime? I'm not sure. I'm pretty sure they're doing studies on it now. Wow, look at that. That's beautiful. Let's see how our filter is going. Should we all green now? Yeah, there we go. Yeah. If there's wind blows the telescope too much and the star image is going to be elongated, I have a threshold value of 8.19. It's actually based on a visual look, and if it gets bigger than that, the star frame is rejected because it means it would elongate the stars a little bit. This way, we're guaranteed perfectly round stars. Gotta have that. So that's what we do. So this massive supernova that we're looking at here is really pretty. That is gorgeous. Wow. Okay. One more takes us to 30, and then we move on. And don't worry, I'm not wasting time, because all this time, Orion's getting higher in the sky. And we'll be able to do some really cool imaging of Orion here shortly, in just a few minutes. All right, we're going to save this and save it exactly as seen. There we go. All right, SkyTourLive.org. Go down to Take Me to Cool Pictures, and you can get this in about 30 seconds from now. So let's get out of this. Let's go over and go back to our low light camera view. All right. So our low light camera view is showing us this, and what we're going to do now is come to Stellarium, back out a little bit, and now if you look where we are in the sky, you'll notice that we are very much near Orion, because Betelgeuse is down here. Now, it is almost straight up, which means we're almost perfect. So I would like to do a couple things. I want to do a lot of things, but let's go for the big ones first. Let's go over here, and we're going to go to Alnatak and capture this region right here. Actually, I'll do it. I'll go here. All right, and you'll see what I mean. So watch the telescope move now over my head here. There it goes. And it's going to start looking almost south. And this is going to be the optimal position for Orion. Right, there's Alnitak right there. All right, right there. And you can see this nebula here. That's called the Flame. And then there's a wall here of dark material. There's this thing sticking out right here. That's the Horsehead. What we're going to do is we're going to head to the east a little bit.
Sigma Orion is over there on the right.
Yeah, I'm going to put that all the way here to highlight the molecular cloud. And there we go. And I'm going to just bring us up just a little bit to bring the rest of the flame in. Because the Horsehead is here. So I can go a little bit lower. I'll keep Sigma Orionis in there. One of your favorite stars.
Yep.
Okay. Alnitak. What is Alnitak? Alnitak is the left star in the belt of Orion. And the other one is up here. That's going to be Alnilam. And the one at the far right up there is Mintaka. All O stars. Okay. Alnitak is a blazing O star. It's probably going to live a few million years more. And then, of course, its destiny will be supernova. And potentially black hole or a neutron star. I'm not sure of its mass. We'll have to figure that out. So what we're going to do now is, now the flame goes off the shot here, but I want you to see the Horsehead Nebula here. So we're going to do this. We're going to do a 25-second shot. We'll keep it at 250 gain. And we'll start coming out of this and go into deep sky mode from our low light mode. And the last image will be, of course, the Jellyfish Nebula that we just took. This is a good night. Let's see what our all sky's looking like. All sky's looking good. There's the winter Milky Way. You don't usually see that, do you? Well, you do here because it's pretty obvious. Look at that right there. Wow. I gotta go back and get ready for this shot. Look at that. Wow. Yeah, so there's the Horsehead. Okay. And it's beautiful. And we have the Flame Nebula here. I got a little of the flame. There's a little more up top, but this is most of it right here. Let's come in here and let's check our enhancements. Make sure, yes, we're good there. And let's... Yeah, okay. That's really pretty.
When you see the Horsehead there and that sort of vertical wall behind it, and then the material to the right of that, that star Sigma Orionis there is what's doing all the lighting up of that nebulosity. Sigma is a beautiful multiple star system.
Up to 6 components, I think, right?
6 or more. A couple of them are spectroscopic, I believe.
Yeah.
Anyway, that's another hot, bright star system, and the energy from Sigma there is what's lighting up, is what's silhouetting the Horsehead and lighting up all that material in the area.
The hydrogen, yeah. Okay, so I want you to understand when you look at this image, okay, all right, you're looking at hydrogen in the area, but this, you're seeing like this sharp edge here, right? What is that? That is actually a large, massive dust cloud that is so big that it spans all of Orion and then some. And it's called the OMCC, the Orion Molecular Cloud Complex. And this dark dust is the place within which life comes. And it's in this dark dust where stars will form in the middle and do things like this. Light up a nebula, all right, and start clearing a cavity like this star is doing. We zoom in, all right, and we only have 3 frames in here right now, so we have to take a few more. But you'll notice that this star that formed in here is lighting up all of this, but it's also pushing away material. It's created a stalk. Here's a stalk. This material at the end is pretty dense, and so it can withstand the radiative pressure of the star's stellar winds, and it pushed away material around this dense area, and this dense area protected the material behind it. And so we get a stalk. Stalks are very common. They're known also as pillars as well. So we see that happening all the time. Now, we can kind of get rid of some of the noise by dropping this down until it's ready. Okay, so if we do that, you can see a little more detail of what's going on inside here with like a little more detail. This looks like an X on here in this dark dust strip. But that's a couple light years in size right there, you know, or maybe a portion of a light year, you know. So that's huge. And then the Horsehead down here, all right, beautiful. And you'll notice as we get more here that the top of the Horsehead is made of a lighter material, as is the top here. At least it's illuminated differently, and it takes the brunt of the light, and what's behind it does not. And again, it could be Sigma Orionis, which is actually responsible for, as Daryl said, exciting this hydrogen. But it could be Sigma Orionis, that star way out here, okay, right here. That's also responsible for just illuminating the dust here and making a reflection off the top of it, you know. And we'll see it in a minute as when we get more data.
Is the Horsehead itself actually a pillar or a stalk?
I was wondering myself, actually, years ago.
The horse's neck is pointing in the basic direction of Sigma, but then the horse's nose is pointing more like toward that bright star above it in the image.
Yeah.
Actually, I was thinking the one to the right.
I was thinking that one, but it's sort of pointing somewhere in between, I guess. If we draw a line, hey, what am I talking about? We can draw lines. Okay. If we take a line and we draw it through the nose, right, like this, then it's pointing somewhere there. Okay? But this, here, if we look at this, and we draw a line over here, let's see. Oops, I can't. Huh? I gotta get out of this to do it. I'm in a total, just a drawing mode. Yeah, okay. So now we can do it. Like if we come this way, we see that it's not pointing directly there. This isn't pointing directly there.
Oh well.
No, it's fine. Because it could be a perspective effect too, you know. Which could be explain the divergence of these lines. It could be something that's actually coming out toward us too. This could be a lot closer to us, for instance, than the base is, and it could be something coming at us. So we don't really know. There might be a study out there, but see, we're up to 8 that have been captured now of these images, and we're starting to see that we have a little wind out there, as you can see. So we're catching a few, missing a few. I'd rather catch good ones than not all of them and have some bad ones. Because, for instance, look here.
Tiny little star right there in the near the top of the horse's head.
That's right. Look at that. Beautiful.
And there's another one in the nose, I think. And,
yeah, there is. There is one up there.
One in the horse's mane.
Right there. It'll show up better in a little bit. I think I could coax that out if I do this. See, we're waiting. There's no excuse for good data. We only have 10 images here. If we went to 20 images, this would look more like this. It would actually look better in here. Hey, Star Voyager, how you doing? That is correct, Star Voyager. We just were talking about how Sigma Orionis. He asked the question, the Horsehead is between us and that nice red nebula behind it. That's right. This is Sigma, and it is actually illuminating, causing the hydrogen gas to glow here. And that's what's going on here. And so it's being silhouetted by the glow here. We would never have known it was there otherwise. Pretty cool. And the top of the Horsehead, you see, has a kind of a whitish hue. That's a glow from probably Sigma, whose light is striking the dust, and kind of like the sun illuminates clouds, Sigma's illuminating this. We have some here too that we've never seen before. Okay.
Can you go to Stellarium for a second?
Mm-hmm.
I forget. Does it show Barnard's Loop?
Yeah. We see that when we go out to get the...
It's very faint, but there it is.
Yeah, we see that when we go out to look at the Boogeyman and Casper the Friendly Ghost.
If you can see that curve of Barnard's Loop there, folks, if you try to follow to the center of that curve, like if that was an arc of a circle, you see you're actually, it's in this general area here, maybe between the Horsehead and the Orion Nebula, down to the lower right.
Mm-hmm.
And that's the big, huge supernova remnant.
Yeah.
Probably been a ton of supernovas in this area of the sky.
Yeah, because this is an area that is right in the middle of the spiral arms where young hot stars are formed, as we know, and it stands to reason there'll be a lot of supernovas and thus dust that is created here from large low mass dying stars and high mass stars that are so massive that they create molecules in their outer hemispheres and then slough them off. This is so cool. Let's go back to the show. Okay, so we're at 14. The halos are due. No one's asking, but I'll just tell you. And good night, Izabela. I said good night to you in the chat, but I'll say it, with my voice. The halos are caused by our imaging system. On our next, for the Benson telescope, which will be 220 miles away from this one, on a mountaintop with other astronomers, that one, hopefully, will not have halos in our images, because we're not going to be using a very fast system like we are here. We're going to be doing a lot of really interesting deep dives on things like the Horsehead, like this guy right here, and other elements that we've never seen. It'll be unprecedented detail. So it'll be like a whole new universe to us.
I know we've talked about this before, but when you look at the Flame Nebula there, I mean, that is not just hydrogen red. There's more going on there. It's paler. It's more of a almost kind of a fleshy pink color, instead of that hydrogen red like you see down by the Horsehead.
Yeah.
And there are stars hidden behind that dark cloud, I have to guess.
Yeah, there are. We've talked about this. This is a dark cloud too.
Yeah.
See, if you look at all the stars here, guys, and then look here, you see, like, how do you suddenly have less stars here? Could that be the actual distribution? Well, yeah, but not likely. What's happening is the molecular cloud is here, and stars. There's the stars that are in here, behind here, in this dark cloud, are actually stars that are very, very powerful. Alnitak, if I recall, is illuminating the flame and causing it to glow. I think we once talked about stars inside the dark here that we don't see that might also be participating in that. It's probably, in reality, it's probably a mix of the two.
Yeah. Well, I guess you would say then it's a mix of hydrogen red and maybe reflection nebula.
Absolutely. There's no doubt about it. And the fact that we have dust overlying this. Now, the red color that we see, the brighter red, is because of the increased density of hydrogen locally in that area. The more hydrogen there is, the more hydrogen atoms can glow red, and the brighter the glow. So here, it's not as bright, and you also have a lot of dust, and you can see at the fringe here, near the extreme top, it's sort of tending to blue. It's tending to blue in some of these regions, meaning that the dust is almost equally as copious as the hydrogen. And so the blue is in the dust is actually causing the dust to be kind of muted a little, or causing the gas to be muted a little bit. That's the way it appears to me. And look, a satellite.
Zoom, zoom.
Yeah. All right. Well, we got 20 shots here. I think this is good. So we'll save this. Let me first do this right now. I'm going to name it. Good. And we'll say Horsehead Nebula. And we'll say target. Okay. And then we'll say save with annotations.
It always amazes me what an easy target this is to a modern astro camera. To the eye. I have seen the Horsehead exactly once.
Yeah.
And that was in a large telescope with, I believe it was a hydrogen beta filter, if I remember right. And it was more like, yeah, I think I see the Horsehead.
Yeah. It's very faint, right?
Yeah, it was like a black on black almost.
Yeah.
You can see it, but barely, and not nearly with the kind of detail and how it pops out here.
Yeah. And then here's things that are totally missing. Is you see this stalk, you can actually see how it winds in and has complexity in this stalk. Again, this looked kind of muted the last camera, and here we can actually see much more detail. It's really quite nice. The Star Voyager asks, this is the true color? If so, why are the stars cyan? Actually, that's a blue color that you're seeing there. And that blue color, let me see if a color correct can change that for you. Well, the color correction kind of shows them as a light blue now. The light blue is the fact that this is all dust, micron-sized particles, okay, 10 to the minus 8 meters in size, and these particles are scattering the blue light from the stars, because blue light is high frequency, and these tiny dust particles love to take in and reflect back this blue light from stars. That's called Rayleigh scattering. Same process as why our sky is blue, but with molecules in our atmosphere of air. So that's, you're seeing the nebula being illuminated by the stars here. Here the stars don't look cyan. They look like their normal colors. This star at the top here is Alnitak. That is an O-type star. It's exceedingly hot. Most of its radiation is given off in the ultraviolet, which explains why this nebula is glowing like it is, and why it has a copious amount of ultraviolet because of its temperature. Okay, so hopefully that explains that. And Star Voyager says, oh, by the same clouds that made the Horsehead. Yes, exactly so. This is dark nebula in here that just happens to be illuminated. And this is dark nebula that isn't illuminated, other than this little top piece here, if you notice. You'll see there's a little bit of a lighter thing down the side here as well, where it's less dense. But let's zoom in one more time, and you can see now. Remember that star that Daryl was telling you in the nose and the main? Well, here's the star in the nose, and here's the star in the main. See how tiny those are? And
I
here,
see another one in that reddish part.
right here.
Yeah, right there.
Yep. And this is that illuminated top section, if you want to call it the top of the head, illuminated by other stars, probably Sigma Orionis, that's off to the side here.
And there's another even dimmer star in the sort of where the I think on the front of the horse's forehead, about where you might imagine
right
his eye
there.
to be. Right there, yeah.
Yeah, maybe. JSEO, hey, glad you could join us. Thanks, man. Yeah, that's true. Beautiful. Okay, well, we've got 28 stacked here, and we'll save it.
As far as the cloud itself goes, I mean, up below the big blue area you see now,
Yeah.
you can see hints of like the turbulence or the mix of the cloud in the darker areas down below it.
This here, you mean?
Above that, to the upper left,
Oh, here?
like that right there.
Oh, yeah. Yeah, let's try one last time here, because I'm really pushing a little bit here. Let's move this down a little bit and see if that helps. No. It actually makes it harder to see. But hey, it's there. Let's see if over-processing it will show us anything. Oh, look at, we have this little shoulder here. Look at that right here. That's cool. Haven't seen that before, but now you see that lit area on top of the horse's head very clearly. Yeah, and there's some right down the middle of the snout, so to speak.
Star in the nose.
Yeah, right there. Right there.
And I still think that's a star
Right
there on the front of
there.
the horse's face.
Maybe there.
Yes.
Definitely there now, and another one right there. There's one here and one here. Yeah, that's really cool. Wow. Okay, so let's now come back out and see what our whole scene looks like. Now, if you look here, look at all the complexity of dust in here. You can see it. It's a major dust complex. You know, all the Orion molecular cloud complex. Really neat. And let me take this down to where it was before. All right, and bring this up to kind of match a little bit. Look at that. Nice. Okay, 32 images. Save. And save exactly as seen. All right. So, we will leave this behind for tonight and go back to our low light mode so we can check out the next thing. Okay. There we go. And let's bring this in. Go to a stellarium. And now, I know people want to see it. We'll get there. Okay, we're going to get there now. We'll do this now. Make this one of our best objects tonight. Let's move to the Orion Nebula and let's see how it looks. it's in prime position, so we'll get the best imagery of it tonight. All right, I'm gonna take off my sweater. Hold on, guys.
I see Barney. Are you there?
Sorry about that. That was probably sounded like a creaky barn door or something, or a screaming ghoul. All right, back. Okay, so let's move a little to the east here. And this eastern motion is going to help us center up. That's good. Do I want to start at the top? I do. I'm going to take us to this area right here. That's called the Running Man. You like the Running Man, right?
Sure.
All right. This is good. And we'll see some of the nebula, then we'll go south to get the rest of it. Okay, so this will be a 25-second photo of this region. We are guiding, we can tell from looking at the numbers here. And then we're going to go into our live stack. That is our previous image. A lot going on in here. A lot to unpack in here, huh? Wow. Now that's something. The Running Man Nebula is part of the Orion Molecular Cloud Complex, as is Orion's Nebula here. And in between them, there's a dust lane in here. So that dust lane is sticking itself. That dust lane is sticking itself in here, and that Reflection Nebula is in the background. That one at the top, and the Orion Nebula is down at the bottom. So that's all one contiguous region, and there's some dust in here too, which may be blocking some of these things from being seen. You know. All right, so we got 2 shots taken. Let's look at our full width f maximum here. Oh, Kate says, wow, it's going to get better, Kate. It's going to get much better. All right, I'm going to bring us up to 9.16. It looks like we can get away with that. You'll see this incredible stuff begin to materialize here as more exposures come in. We're going to color correct first. All right. Again, a lot to unpack here too. Let's take that there. Let's take this down to here. Yeah. So you see these filaments are coming in beautifully right down here. They're starting to show very nicely. Now this greenish blue here is a little different. This down here is ionized oxygen in this part of the nebula. Up here, this rich blue here is mixing with potentially some ionized oxygen, but that rich blue is the reflection nebula that's occurring when the starlight is reflecting off of the dust particles. All right, that's making this blue primarily. But deep inside of that blue nebula, we have a regular emission of hydrogen going on deep inside. Now, you'll say, but that doesn't look like the red either. No, it doesn't. But that's because we have the blue that's being ionized in front of it. And we're seeing that red through it. And because of that, we're seeing that we have an incredible amount of this mixing, color mixing going on. So it's like the universe is teaching us art class as well. And how colors mix. How light mixes.
Star Voyager has a question of you.
What Bortle level is this telescope? John Bortle came up with I know you know this, Star Voyager, but I'm telling everybody. John Bortle came up with a scale for trying to measure sky brightness. If you're in the middle of a city, it's a 9 because it's really bright white. You can barely see certain stars, and there's criteria. 0 is like in the middle of the ocean where no islands are within 1,000 miles of you. So that would be kind of 0. In a Bortle 0 sky, you'll notice things like sky glow, the glow of the molecules themselves after the sun goes down. You'll see those in your photos. You say, what is that green glow? Where'd that come from? And why is there an orange glow? That's to be the sodium glow, the sodium atoms. So, but Bortle 1 and 2 are very, very dark skies. We're in a Bortle 3, where we are now. I will show you in our all-sky cam, the view. Okay, here is our view right now. It's only a 12-second shot. This is the lights of Phoenix, about 80 miles to our east-southeast. Now, I'm in Connecticut, and I'm running this telescope that you see here 2,600 miles away to bring this to you. And so this glow is something I certainly don't see here. My skies all look like this. Okay, I'm in Bortle 5 skies. Kind of bordering on Bortle 4.5, 5, 5.5, sort of in there. So let's say 5. Okay, and out here, you can see the winter Milky Way horizon to horizon. This is something you can see with your eyes. You don't have to look hard to see it. Down here, it gets a little lost because we're looking through more air, and we have some interference by the sky in Phoenix down here that are causing this light dome to appear. Now, we don't have a lot of moisture in here. If we did, then this light dome could conceivably be out here, but we've never had that. So this is pretty cool. And your Star Voyager's in Bortle 2. So brighter skies. And where we're going want to go in Benson, the sky is marginally brighter than this. I'm sorry, dimmer than this. No, sorry. The stars are marginally brighter. The Milky Way is marginally brighter, so it's a slightly lower Bortle level there. Okay. Now we're also using special filters. Look at that. Go away for a couple seconds and come back, and magic occurs. Look at this beautiful complexity. This is the Running Man Nebula here, so named because this looks like a running man. Arnold Schwarzenegger, stick around. Looks like a running man. What's he chasing? I don't know. All right. And then we have this beautiful cloud here. And it shares illumination from Orion Nebula stars, and glows of their gas are actually reflecting just straight off dust particles. So we're getting straight reflection. And where we see more complexity is where we see the material, the dust in here, scattering more of the blue light from the stars in here. And that makes this a very blue region. All right. That's just beautiful. Now, a blue reflection nebula and the doubly ionized oxygen regions are different from each other. They look different, but it's sort of hard to tell. Okay. And the camera response can be responsible for confusing you too. That's beautiful. Wow. Okay. We're waiting for a few more to come in here.
Kate, you ain't seen nothing yet. Running Man is just preamble.
It's true.
I believe M43 is,
What is this right here?
you know, that teardrop shape, kind of crooked teardrop.
You believe it? What? Oh,
Excuse me?
You said you were saying, yeah, this is M43 right here.
Yes.
Yeah.
Curious, the dark wisps in front of it and down under it.
Yeah.
That's M43 anyway, and then
Yeah.
M42 is the main nebula down below,
Yeah.
which we're only seeing part of right now.
Yeah, we'll get to more. Roxana, that's what you're asking about, was this thing here. That's actually a piece of this overall nebula. This is Messier 42. This is Messier 43. This is NGC, I want to say 1999, but I think that's actually not it. I think 1999 is the little keyhole nebula down below, the rubber stamp. Let me just go back here just to get that right. Oh, 1977. Okay, so yeah, I knew it was two numbers. This is 1977, and then there's something down below called 1999, which is this thing called the 13th Pearl. A very, very odd shaped nebula. Okay, 16 of these. That'll be good for here. Let's see if we get the 17th.
Looks like your wind is getting worse.
Yeah, it's coming and going, see? Alright, we got 17. I'll save that. But I think I better identify first. I could just type it in, but I'm just doing this. Let's isolate. There we go. And we'll say Running Man. We'll give it the target name. Save with annotations. And then we're done. And now we come over here and save it. Save it exactly as seen. Oh yeah, this is something. Let me, while we're waiting for another one to come in, let's just, let's get rid of this for a second here. And let's just take this in. Wow, that's something. Let's push this now. Watch what happens. There'll be a lot more out here. See all that brown dust? This is all molecular dust out here. Look at the streaks and the turbulent eddies. It's almost like you're looking inside water with dye in it. But instead, we're looking at the interstellar medium. And I think that's... It's got an allure all its own. Alright, let's bring that back so we can richen this up. Rascally Rabbit, how you doing, man? What's interesting is that when we're looking here, we haven't captured any satellites coming through here. Normally we do. But they're actually down just out of sight here. And there's geosynchronous satellites down here below the image where we see the next shot. Okay. So let's go and do this. Dock it up. And
Because we are on or very near the celestial equator.
yeah, we are. So let's now see exactly the scene. Okay. So this is 22 shots. Let's come out of here now. Let's also, while we're here, take a moment to show you what's powering this nebula. And that's down here. I want to bring my telescope back here. Alright. And let's go south. Go south, young man. And bring the nebula up into the view. There we go. We're going to go way up. I'll stop in the middle here just to zoom in and show you the stars in the middle. This is the trapezium. And we're going to bring them way down in brightness so I can show them to you. This quadruplet of bright stars. Let me do that. This quadruplet of bright stars is powering this nebula. And there's not just 4. There's, oh gosh, maybe even more than 6 stars in here, some not visible to us, that are powering all this. Okay, so that's pretty cool. And so that's causing all this to be illuminated. Alright. So now what I'll do is I'm going to move us south again. Because you'll like what's coming next. Java Joe, how you doing? Color or mono camera? Well, okay, it depends what you want to do, Java Joe. If you want to do narrow band imaging, it's probably best to get a mono camera and then combine them. If you want to do a one-shot color, then you can get beautiful shots like this. What we're going to do is we're going to use a color camera in mono mode, and we're going to take it and just take monochrome images, and recombine them later to when we do the narrow band with the other telescope. And that will be very helpful to us. I think from here, I'm going to do it here because it has the whole nebula in view. And we'll do a 25-second shot here. Alright, we're guiding, so we're good. So let's go from low light to deep sky mode. Okay, that's our previous image. Now I could clear it. I could hit clear if I want to, but I like to let you see it. And the next image is going to be like from here down, and you'll see what's below it too. So you get it. And you'll see it's more noisy because it's only one image. We stack more and it becomes, yeah, there's all those satellites. We stack more and it becomes more smooth looking. Now, our exposure is 25 seconds. Now, these satellites, they never seem to leave the view. They move across, all right, but what's going on? Well, we're tracking the stars. If I turned off the tracking, the stars would blur, but you'd see a dot here, a dot here, no, maybe not there, You'd see a dot here, a dot here, a dot there. And you'd see all the stars trailing, but then those dots would be there because now we're not tracking. We're just looking at the same spot. And that's what those satellites are doing. They're in a geostationary position, looking at the same spot all the time. But Earth's rotating. And as it's rotating, we're following the stars. So for this thing to stay over the same spot on the Earth, it has to trail when we're following the stars. Right? Because the stars are shifting behind them. As they're staying over the same spot on the Earth. They're rotating with the Earth. So they stay over the same spot.
There is a well-known time-lapse video taken from the Very Large Telescope Array at the European Southern Observatory, the ESO, where as you watch this time-lapse at a certain point, you can see geosynchronous satellites come into view, one right after the other. About 5 in a row pop up in one section of it.
That's very cool. Very cool. Yeah, we got a lot of people are enjoying it tonight, which is nice.
Say, folks, if you like what you're seeing, please hit that thumbs up button.
Yeah, we definitely want that.
Helps the algorithm.
Yeah, help us showcase on there, so we get other benefits, and we can do things to bring you all kinds of other neat opportunities. Ronald asks, that's Earth Radio. On the finished product, how do you remove the lines? Well, as you'll notice, the lines are getting a little dimmer. The longer exposures we do, the more good data overlays this bad data. So, as time moves forward, these lines will all but vanish. We'll lose them over time. Really pretty, it looks good. Okay, I'm gonna drop this down a little bit. Now you'll see here, you can see this beautiful complex dust up here. You know, let me do this. Let's zoom in, shall we? Look at that. That is really incredible. You gotta wonder what's really going on in there. Extremely complex. Let's see if I can dig even deeper.
Ronald, it is the color of doubly ionized oxygen.
Yeah, it's close to what the reflection nebula looked like, Ronald. But the reflection nebula are more of a cobalt blue. This is more of a teal. You're more than welcome. Goblin says, kind of remind you of a cup of cotton candy.
Excuse me again for a moment, please.
Yeah.
Right back.
Java Joe makes a rather interesting observation. He says, I envy the future explorers that will get to fly by these amazing things in space. Don't envy them too much, and I'll tell you why. Because if you were flying by this in space, you wouldn't even see it. We're doing a time exposure of 25 seconds. Your eye doesn't work that way. So you wouldn't know you're in a nebula. You might not even see it. You might just see black space around you. You know? David Gala says, supernatural. Thanks for the show. Oh, of course, man. Glad you're enjoying it. It does look really kind of amazing, doesn't it? Look at how beautiful that is. Now let's we have the Great Nebula in Orion. We'll save that as a target name too. Save the image annotation. So the image going up right now is this one with the annotations on it, so you can see what they are. All right, now let's bring this back now. See that? We have so much dynamic range. We can go down to almost nothing or just pump it way up. Look at all that dust. Look at the dust out here. Look at that line right there of ionized, doubly ionized oxygen up against a brown dust cloud. That's incredible. Yes, this whole thing is Measure 42. This little guy has its own name. That's Measure 43. The thing we shot earlier up above, that was NGC 1977. David Galich, thank you, man. Thank you so much. Every little bit helps us. It all goes into our Benson fund. Our Benson fund to get our new telescope out there. It's a Celestron 11 with a filter wheel. I bought the filter wheel myself with my money. And then we're putting a set of a filter suite on the filter wheel. We're going to have a spectral analyzer on there too, so that we could take spectra of stars like this and actually identify what's going on in their spectrums. And that will help. You'll learn all about that here when we do this. And then, so we're going to have narrowband imaging, 3 sets of narrowband filters, 3 narrowband filters, a filter like this one, which is called the UHCS filter, and then we'll have the spectral analyzer, and that's 5 positions. Now, eventually, we'll change to a 7-position filter wheel, and that'll allow us to have like a dedicated black cover, called a dark frame. We could take the spectral analyzer out and just put in a dark frame there, but not needed, Okay, 19 images. We'll go to 20.
Back.
Hey there.
I'm going to have to call it a night pretty soon here, Mark.
Okay, no problem. This is the last object.
Okay.
So there's 20. So we'll save it. And save exactly as seen. That was right before this, Ronald. We did the Running Man. Okay. We should go to 22 and then we'll be good. There we go. Okay, now on another night, what we'll do is we'll go south of this, and we'll also go to the left of this out here. There's beautiful features in the dark dust out here that are just amazing to see. All right, but for now, we're good here, and we're going to save it exactly as seen. There we go. So this image, which I'll bring up, this image is the one, not that one, sorry. This one, sorry. This is the images that'll be up on the server here for you. And that's a free one. Now, when we do the final processing, we're going to put this one together with the one above, make a mosaic of the two. Those are for, we do those for the Patreon subscribers. And what we do is we remove these halos around the stars. This particular one is kind of tough in what's called the lower sword of Orion. This halo is tough because it has stars inside of it, but we still get it out. Java Joe, yeah. Can't wait to hear about it. Alright, so that's our static shot. And our shot there, okay. So yeah, so basically, this goes here. And we can just bring this to the peak. Get the most dark out of it without losing data. Look at that. I think I should do this. Oof, that's beautiful. Alright, we'll let it go to 25. Then we'll take that picture, save it, and then we will call it a night. I think we did quite a lot of good objects.
Yeah.
So we'll save. Save exactly as seen. Alright, guys. Well, there you go. Orion Molecular Cloud Complex, Nebula. It's like a blister on this dark nebula region. And that is going to be it for tonight. I hope you guys enjoy coming out here and have enjoyed it. I will now go into our low light mode and take us to our rest. All right. Thanks, guys, for coming out. I hope you have a good night, and we will see you on the very next stream, our SkyTour live stream. Thanks for coming, and we'll see you later.
Good night, everybody.
Good night, folks.
I'm going to go finish my laundry now.
Okay. Good night, everybody.
Good night.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming light for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across dream, living real, like a gleam. Lift your eye up so high, across the stars beyond the sky. SkyTour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. SkyTour is bringing the views, every night feels brand new. Lift your eyes to the skies, universe in all its light. SkyTour is bringing